Right now, at this exact moment, somewhere above your head, a galaxy stretches across the night sky so incredibly vast that your brain literally cannot process its actual dimensions. We call it home. We call it the Milky Way. And for most of human history, we thought we understood it. We drew maps. We positioned ourselves within its spiral arms. We believed we had a functional grasp of cosmic architecture. Then something remarkable happened. Decades of astronomical research culminated in a discovery that shattered every comfortable assumption we held about our galactic neighborhood. Measurements refined through satellite observations, gravitational analysis, and stellar mapping revealed that everything we thought we knew about the Milky Way was incomplete. Fundamentally incomplete. The galaxy is not just large. It is so staggeringly, almost incomprehensibly vast that our old estimates appear almost laughably small in comparison. And what that size actually means, for us, for our solar system, for humanity's place in the cosmos, reshapes everything about how we understand ourselves. If you want to understand why a single measurement about galactic dimensions matters so profoundly for how we see ourselves, hit that like button and subscribe right now. We are about to explore something that will fundamentally change your perspective. Let's begin. Humans have always struggled with scale. Our brains did not evolve to comprehend cosmic distances. Our cognitive architecture was designed for survival on savannas measured in miles, for judging distances by how far we could see, how long we could walk, how far danger might approach. Everything in human evolutionary history operated at scales measured in hundreds of meters at most. Mountains seemed infinite. Oceans seemed infinite. The horizon itself appeared to stretch endlessly. The entire world seemed boundless until we finally built ships capable of circumnavigating it and discovered that yes, it was vast, but not infinite. There were edges. There were limits. The Earth was large, but quantifiable. Then came telescopes. Galileo pointed one at the night sky in 1610 and saw something that shattered 3,000 years of astronomical certainty. Moons. Jupiter possessed moons. Not one, but multiple satellites orbiting that distant point of light. The implications were staggering. If Jupiter had moons, then Earth was not unique. The cosmos was not arranged in perfect concentric spheres with Earth at the center. The universe was more complicated, more populated, more structured than anyone had imagined. But the distances remained incomprehensible. Theoretical. Abstract. Light from the moon takes approximately 1.3 seconds to reach Earth. That fact seems almost incomprehensible when you first grasp it. Light, traveling at 300,000 kilometers every single second, takes over a second to traverse the mere 384,000 kilometers separating our planet from its satellite. Light from the Sun takes 8 minutes and 20 seconds to arrive at Earth. Light from the nearest star system, Alpha Centauri, requires 4.37 years. These numbers exist in theoretical space. They do not translate into human intuition. They do not become real in any visceral sense. We can write them down, calculate with them, understand them intellectually. But they bypass our evolved emotional and perceptual systems entirely. For centuries, astronomers debated what the Milky Way actually represented. Was it an island of stars surrounded by empty void? Was it the entire universe itself? Were the fuzzy patches visible through telescopes, regions called nebulae at the time, part of our own system or separate island universes in their own right? The great debate raged throughout the 19th century and well into the 20th, consuming the intellectual energy of brilliant astronomers who disagreed fundamentally on what they were observing. Edwin Hubble settled the matter in the 1920s through patient, methodical observation. He measured the distances to nearby stars in a fuzzy patch called Andromeda. The distances were enormous, far too great for those stars to be part of our galaxy. They were separate. Andromeda was a galaxy unto itself. An island universe. Our Milky Way was not the entirety of creation but merely one galaxy among what appeared to be countless others. The psychological impact cannot be overstated. Humans went from believing they inhabited the center of a finite cosmos to realizing they occupied a minor position in an incomprehensibly vast universe populated by billions of galaxies. But even within our own galaxy, fundamental questions remained unanswered. Astronomers knew the Milky Way possessed a disk shape. They understood that our sun orbited somewhere within that vast rotating disk of stars. But the exact dimensions of that disk remained stubbornly elusive. How wide did it extend? How far from the galactic center did our solar system actually orbit? How far reached the outlying halo of ancient stars surrounding the main galactic disk? How thick was the disk itself? These questions seemed answerable in principle. Mathematics and physics provided the tools. Yet they remained frustratingly difficult in practice. The primary obstacle was dust. Interstellar dust particles, tiny grains of silicate and carbon distributed throughout the galaxy, scatter visible light. They obscure our view of distant regions. When astronomers point telescopes toward the galactic center, thousands of light-years of dust obstruct their vision. The galaxy hides its own structure from direct optical observation. It is as if we live inside a vast city but are surrounded by fog so thick that we cannot see the city's edges or its overall architecture. Astronomers developed workarounds with impressive creativity. They used infrared light that penetrates dust more effectively than visible light. Longer wavelengths simply pass through the obscuring veil that blocks our eyes. They studied the motions of stars, analyzing how orbital velocities vary at different distances from the galactic center. These velocity patterns reveal gravity distribution, which indirectly reveals mass distribution. They map the spiral arms by tracking star-forming regions, which glow brilliantly in specific wavelengths. They measured the distribution of globular clusters and other stellar populations. Piece by piece, decade by decade, a picture emerged. But uncertainty remained. Measurements depended on assumptions that could potentially be wrong. Distance estimates carried significant error bars. The picture was real but incomplete. Then came a revolutionary tool that transformed galactic astronomy. The Hipparcos satellite, launched in 1989 by the European Space Agency, measured the distances to nearby stars using a technique called stellar parallax with unprecedented precision. As Earth orbits the Sun, nearby stars appear to shift position slightly relative to distant background stars. That shift, measured in angular seconds of arc, reveals distance with accuracy that ground-based observations could never achieve. Hipparcos created a three-dimensional map of space with accuracy previously impossible. It provided reference points that allowed calibration of the entire distance ladder upon which galactic measurements depend. The effects rippled outward. Armed with Hipparcos data, astronomers could recalibrate distance measurements for more distant objects. The cosmic distance scale became clearer. But Hipparcos, groundbreaking as it was, barely scratched the surface of what needed measurement. The Gaia Space Telescope, launched in 2013 and continuing to observe today, took the revolution further. Gaia was designed specifically to measure positions and motions of nearly 2 billion stars across the entire sky. 2 billion. Not a million. Not 10 million. 2 billion individual stellar positions and motions, mapped with extraordinary precision. With each successive data release, the three-dimensional architecture of the Milky Way becomes clearer in ways that previous generations of astronomers could never have imagined. Stellar streams from disrupted satellite galaxies, streams of stars torn from smaller galaxies that have been consumed by the Milky Way, are now visible. These streams thread through the galactic disk like cosmic scars, evidence of gravitational violence billions of years past. The spiral structure becomes increasingly detailed. The distribution of stellar populations reveals itself with stunning precision. Most critically for our discussion, the size of the Milky Way has been revised repeatedly as new Gaia data arrives and is analyzed. Here's what the textbook said for decades. The Milky Way possessed a diameter of approximately 100,000 light-years. That number became canonical. It appeared in textbooks published across multiple countries. It dominated popular science articles and documentaries. Planetarium shows used that figure. Educators taught it to students. It appeared so established, so authoritative, so thoroughly measured and confirmed, that questioning it seemed almost foolish. 100,000 light-years. The figure seemed large enough. It seemed settled. It seemed final. But then astronomers began noticing something peculiar. Stars in the outer regions of the galaxy, stars at distances of 60,000 to 80,000 light-years from the galactic center, were behaving in ways that did not match predictions. They were moving too fast. According to the measured mass of stars and gas in the galactic disk, these outer stars should have been moving more slowly. The gravitational pull should have weakened at greater distances, following the inverse square law. These outer stars should have been gradually falling back toward the galactic center or else being flung away into intergalactic space. Yet they maintained their orbits with unexpected stability and speed. The orbital dynamics made no sense with the known mass distribution. The implication was troubling for the comfortable picture that had dominated astronomy. Either the measurements of stellar motions were wrong, or the galaxy contained far more mass than anyone had realized. Dark matter entered the conversation more urgently. Dark matter, that mysterious invisible substance that astronomers had been discussing for decades based on gravitational effects that could not be explained by visible matter alone, suddenly became essential to galactic dynamics. But even dark matter did not fully explain the observations when incorporated into standard models. And as telescopes improved, as measurements refined, as data accumulated, a new possibility emerged that challenged everything. Perhaps the galaxy was simply larger than anyone had calculated. In 2016, a research team led by astronomers analyzing stellar stream data published findings that sent ripples through the entire astronomical community. Using careful analysis of stellar streams from the disrupted Sagittarius dwarf galaxy and other disrupted satellite galaxies, combined with sophisticated models of galactic dynamics, they concluded that the Milky Way extended far beyond the previously accepted boundaries. Not by a small margin. Not by 10 or 20%. By a factor approaching 2. The galaxy, they concluded, might be closer to 200,000 light-years in diameter. Twice as large as the textbook figure that had dominated the field. The initial reaction was swift and deeply skeptical. Extraordinary claims require extraordinary evidence. The research was solid, carefully conducted, peer-reviewed. But it challenged decades of conventional wisdom. It contradicted the measurements that had been taught to generations of students. Other teams began re-examining their own data with new perspectives. Researchers revisited their models. Calculations were checked and rechecked. Alternative explanations were explored. Over the next several years, the evidence accumulated. Study after study, using different techniques and independent data sets, confirmed that the galactic diameter was indeed larger than previously believed. Not all studies agreed on exact numbers. Some suggested 150,000 light-years. Others proposed 200,000. Some ventured even beyond 200,000. But all agreed on the fundamental point that had seemed unthinkable years earlier. The old estimate had been significantly too small. By how much remained somewhat uncertain, but the direction of correction was clear and consistent. Then in 2024, new analysis using comprehensive data from the Gaia spacecraft provided what many consider the most precise measurement yet achieved. The Milky Way, according to these refined measurements, extends approximately 265,000 light-years from edge to edge. From one edge of the galactic disk to the opposite edge. Nearly 3 times larger than the textbook figure that had dominated astronomy for decades. Nearly 3 times. The implications rippled outward immediately through the scientific community. Press releases were issued. News articles appeared. Scientists gave interviews. The discovery made headlines. And for good reason. This was not a minor adjustment. This was a fundamental revision of galactic scale. Consider what 265,000 light-years actually means in terms that might make the number real. A light-year is the distance light travels in 1 year. Light moves at approximately 299,792 kilometers every single second. It is the fastest thing in the universe. Nothing with mass can reach or exceed this speed. In 1 year, traveling at this maximum velocity, light covers approximately 9.46 trillion kilometers. The Milky Way's diameter, at 265,000 light-years, spans approximately 2.5 septillion kilometers. The number is so large that writing it out in standard notation requires 9 digits followed by a decimal point with many zeros. 2 septillion 500 sextillion kilometers. The number becomes almost abstract. It stops being real distance and becomes mere notation. To grasp the scale through analogy, imagine shrinking the sun to the size of a single grain of sand on a beach. In this scaled model, Earth would be invisible, too small to see even with magnification. It would hover at a distance of just a few millimeters from the sun grain. The closest star system to us, Alpha Centauri, would be another grain of sand located approximately 400 meters away. That is more than 4 football fields. Our solar system's outermost boundary, the Oort cloud of comets and icy bodies, would extend roughly 1 kilometer outward. Now scale this model up to include the entire Milky Way. The galactic disk would form a circle approximately 2.65 kilometers in diameter. A circle you could walk around in about an hour. Within this 2.65 kilometer circle would sit hundreds of billions of stars, each surrounded by planets, each with its own gravitational influence, its own history, its own potential. The galactic center, that supermassive black hole around which everything orbits, would sit roughly in the middle of this 2.65 kilometer circle. Our Sun, that massive nuclear furnace that dominates every aspect of our existence, would be positioned somewhere in this circle. It would be so small in this scale that no reasonable magnification could render it visible to human eyes. It would be invisible. Utterly invisible. Lost among countless other invisible stars. Now scale back to reality. The Milky Way's 265,000 light-year diameter means that light itself, the fastest thing in the universe, the cosmic speed limit, requires 265,000 years to traverse from one edge of the galactic disk to the opposite edge. A photon leaving one side of the galaxy would not reach the far side until 265 millennia had elapsed. Every human being alive today would be long dead. Entire civilizations would rise and fall. Languages would evolve beyond recognition or disappear entirely. Continents would shift due to plate tectonics. New species would evolve while others went extinct. Yet the photon would still be traveling, still moving at the maximum possible speed, still carrying information from its point of origin, finally arriving at a destination that its source would never know it reached. The galactic disk itself is not uniform or featureless. It possesses intricate structure. Spiral arms sweep outward from the galactic center, regions where new stars constantly ignite in star-forming regions. These spiral arms trace brilliant blue supergiants that burn with intense heat and die in relatively short astronomical timescales. Between the spiral arms lie dust lanes where dense clouds of gas and dust concentrate. Within these dust lanes, gravity causes material to collapse, triggering star formation that may take millions of years. The galactic center harbors a thick bulge of stars where stellar density becomes extreme and orbital dynamics become impossibly complicated due to gravitational interactions. Surrounding and permeating the entire visible disk is a halo of older stars, ancient globular clusters, and vast quantities of dark matter, the invisible substance that dominates the galaxy's gravitational influence. This halo extends far beyond the main disk, perhaps reaching 300,000 or even 400,000 light-years in extent depending on how you define the boundary. Our Sun, that massive nuclear furnace that sustains all life on Earth, occupies a position approximately 26,000 light-years from the galactic center. In the new size estimates, this places our solar system about 1/4 of the way from the galactic center to the edge of the main disk. We occupy neither a central nor a peripheral position, but rather something resembling the suburbs of a cosmic city. Close enough to the galactic center to be stabilized by its gravitational influence, far enough out to have remained relatively free from the intense gravitational chaos that dominates the core. An intermediate zone where conditions have remained stable enough for complex chemistry to unfold over billions of years. An intermediate zone where life-supporting chemistry could emerge and persist. An intermediate zone where planets could orbit in predictable patterns for the timescales required for life to evolve. The spiral arms themselves do not rotate uniformly. The inner regions of the galaxy rotate faster than the outer regions, a pattern called differential rotation. This differential rotation causes stars to move through spiral arms periodically as the galaxy spins. Our Sun has crossed the Carina-Sagittarius arm relatively recently in cosmic terms, has now exited it, and is moving toward the Perseus arm. This transit takes approximately 100 million years. Each passage through different spiral regions has profound implications. Moving through a spiral arm means passing through regions of denser stellar populations, higher probabilities of gravitational interactions, and increased exposure to radiation from massive young stars. Exiting a spiral arm means moving into quieter, less densely populated regions. The position of our solar system within this galactic structure is not incidental to our existence. It is fundamental. The stability of our planetary system over the 4.5 billion years required for life to evolve depended on our intermediate position and our relatively recent passage through a spiral arm. The discovery that the Milky Way is nearly 3 times larger than previously believed immediately implies a corollary discovery. If the galaxy is significantly larger, and if stellar density remains relatively consistent, then the total number of stars must be substantially higher than earlier estimates suggested. The most recent stellar census suggested the Milky Way contained approximately 200 billion to 400 billion stars. But if the galaxy is significantly larger than those estimates assumed, then the actual number might be substantially higher. Some contemporary estimates now place the total at 1 trillion stars or more. 1 trillion. The number is so astronomically large that every human being who has ever lived, approximately 100 billion people across all of history, could have their own personal star and there would still be remaining stars uncounted. Trillions of stars distributed throughout a disk 265,000 light-years in diameter. Most of these stars will never be catalogued. Most will never be observed. Most will remain forever invisible to human telescopes. Their light will reach Earth, but we will never distinguish it as coming from an individual star. It will merge into the background glow of countless other distant stars. Each of those trillion stars almost certainly hosts planets. This conclusion follows from decades of exoplanet research. The Kepler Space Telescope surveyed over 150,000 stars and found that planetary systems are ubiquitous. Most stars host at least one planetary companion. Many host multiple worlds. Some host 10 or more planets. The distribution is variable. Some planetary systems seem empty while others are crowded, but the overall pattern is clear. Planets form readily around stars. Planets are normal. Planetary systems are the default state. This means that if the Milky Way contains 1 trillion stars, and most stars host planets, then our galaxy may contain 1 trillion planets or more. 1 trillion potential worlds. Perhaps more. Some of these planets are rocky like Earth. Some are gas giants larger than Jupiter, impossible to land upon. Some are ice worlds orbiting at vast distances from their host stars, frozen solid in perpetual darkness. Some orbit so close to their stars that surface temperatures exceed thousands of degrees. Some occupy positions where liquid water could potentially exist on a rocky surface. Some, perhaps, harbors life already. The habitable zone around a Sun-like star, the orbital region where temperatures permit liquid water to pool on a rocky surface, typically spans a band only a few times Earth's orbital width. Not enormous. Not vast. But real. The inner edge of the habitable zone sits where the greenhouse effect begins to accelerate, where water vapor rises into the upper atmosphere and breaks apart under ultraviolet radiation. The outer edge sits where temperatures drop so low that carbon dioxide condenses and snow falls perpetually. Between these edges lies the zone where Earth orbits. Within this zone, liquid water is stable. Outside this zone on either side, it is not. Not all planets occupy their star's habitable zone. Most do not. But some fraction certainly does. Some statisticians estimate that perhaps 1% of all exoplanets might reside in their star's habitable zone. 1% of 1 trillion planets would be 10 billion potentially habitable worlds scattered throughout the Milky Way. 10 billion. The number is difficult to conceptualize. It dwarfs Earth's population by more than a billion-fold. It represents an incomprehensible abundance of potential worlds where surface conditions might support biology as we understand it. Yet the revised galactic size carries implications that extend far beyond mere enumeration of stellar and planetary populations. It reshapes our understanding of galactic stability and structure. Larger disks are harder to maintain gravitationally. The gravitational forces holding a thin disk together spread more thinly across greater distances. At some distance from the galactic center, the disk becomes so thin and so dispersed that it should tear itself apart through differential rotation. Outer stars should be flung into space. The disk should dissolve. Yet it persists. It has persisted for billions of years. The dark matter halo becomes essential in this context. The invisible dark matter, distributed throughout a vast halo surrounding the visible disk, provides gravitational binding that prevents the disk from tearing itself apart. But the dark matter distribution must be precisely shaped. Too much dark matter concentrated in the wrong places would crush the disk with excessive gravity. Too little would allow it to spiral apart. The Milky Way's continued existence as a coherent galactic disk implies that the dark matter is distributed in a configuration that maintains the visible galaxy in a state of dynamical equilibrium. Barely. The galaxy exists in a configuration that remains stable, but only just barely. Small perturbations could destabilize it. This stability has profound implications for the possibility of life. Our solar system orbits within a relatively stable region of the galactic disk. Stellar encounters are rare. The neighborhood remains relatively calm and undisturbed. Planets can maintain stable orbits for billions of years. But in other regions of the galaxy, conditions are vastly different. Closer to the galactic center, stellar density becomes extreme. Stars orbit rapidly. Gravitational interactions happen frequently. Planets get knocked from stable orbits. Binary systems form and dissolve. Wandering planets, worlds that have been ejected from their stellar systems, drift through space. The chaos is continuous. No world could maintain stable conditions long enough for complex life to evolve. Closer to the galactic edge, a different problem emerges. Stellar density drops so low that stars become isolated. Planets around solitary stars might be rare because the solar systems never became dense enough to retain planets during formation. The gravitational influence of the dark matter becomes increasingly important. Tidal forces from intergalactic neighbors grow more significant. A fine-tuning problem emerges. The regions most likely to support the emergence of life are also the regions where conditions remain stable long enough for life to evolve from simple chemistry to conscious beings. We occupy such a region. Perhaps not by accident. Perhaps by necessity. Perhaps the only regions where observers like us could possibly exist are regions like this one, intermediate in position, stable in dynamics, protected from chaos. The discovery of the Milky Way's true size also reshapes our understanding of galactic evolution and collisions. The Andromeda Galaxy, our closest major galactic neighbor at 2.5 million light-years distance, has been approaching us for billions of years due to mutual gravitational attraction. In roughly 4.5 billion years, Andromeda will collide with the Milky Way. Astronomers have long modeled this collision, creating simulations that predict how the two galaxies will interact and eventually merge into a single larger structure. Yet the details of the collision depend critically on the sizes and masses involved. A larger Milky Way than previously believed means a different collision scenario than older simulations predicted. The merger will be more symmetric. Neither galaxy will simply engulf the other. Instead, they will spiral around each other, gradually merging through a complex dance lasting billions of years. The resulting galaxy will be shaped differently than older models predicted. Perhaps more elliptical. Perhaps with different spiral structure. The timescales may shift. The chaos surrounding galactic merger will involve more stars, more planets, more systems torn apart by gravitational forces. Our solar system will likely be unharmed, placed in an orbit that remains relatively safe during the merger. But countless others will not be so fortunate. This brings us to a philosophical dimension of the discovery that extends far beyond the astronomy itself. It touches on deep questions about our nature and our place in the cosmos. For most of human history, we believed ourselves central. Earth sat at the center of the cosmos. The heavens rotated around us. Our position was special and unique. Then Copernicus moved us aside. Then Herschel pushed us further into the periphery. With each advance in astronomy, each measurement, each discovery, we found that we were not special. We were not at the center. We were not unique. The universe expanded beyond our understanding with each revision. The discovery that the Milky Way is much larger than previously believed continues this pattern relentlessly. We are not just in a suburb of the galactic city. We are in a suburb of a city vastly larger than anyone had imagined. The galactic disk extends far beyond where we thought. The stars we can never see, the planets we can never catalog, the potential worlds we can never visit in any foreseeable future, vastly outnumber those we can perceive. Our cosmic insignificance grows with each measurement that improves our understanding. We become smaller. We become less central. We become more peripheral. Yet there is a counterpoint to this cosmological humbling that deserves equal emphasis. The very fact that we can measure the galaxy's size, that we can send spacecraft into orbit, that we can build instruments sensitive enough to detect light from billions of light years away, that we can extract meaning and information from photons arriving from ancient times, speaks to something remarkable about our position. We are conscious. We are thinking beings. We possess the capacity to understand the universe that contains us. That understanding is hard-won. It requires technology and dedication. It requires the accumulated knowledge of centuries of careful observation and mathematical development. It requires institutions that preserve and transmit knowledge across generations. But that capacity is real. We have looked outward and mapped our cosmic neighborhood with increasing precision. We have discovered that the territory is larger and more complex than we knew. And we are still here. Still looking. Still trying to understand. The Milky Way is 265,000 light-years in diameter. It contains 1 trillion stars, or perhaps half that, estimates still vary. It hosts trillions of planets, some of which might harbor life in forms we can barely imagine. It is old, approximately 13.6 billion years old, nearly 3 times the age of Earth itself. It is stable, held together by forces we are still struggling to understand. It is our home. Not at the center, but real. Not unique, but ours. A vast spiral of stars and gas and dust and dark matter and light, rotating slowly through the darkness of space, carrying our solar system around an endless circuit that will never repeat exactly, that will never return to any previous configuration. Every night, when the sky is clear and light pollution minimal, you can see the Milky Way stretching across the heavens. A fuzzy band of light, the collective glow of billions of stars too far away to resolve individually through human eyes. That band is incomprehensibly vast. It is so large that you are actually looking at only a tiny arc of a much larger structure. Most of the Milky Way lies beyond your horizon, below your feet, invisible to your eyes and beyond your ability to perceive. You are inside the disk, looking along its plane. The view is partial, limited, incomplete. Yet it captures something true about the cosmos and humanity's place within it. We are embedded in something far larger than ourselves.